Okay, hello. You should be able to hear me now. So let's get started here. Give me a thumbs up if you can hear me, so I know the stream is coming through. All right. Okay, thank you very much. So what we're going to talk about today is gravitation. The different topics of that. One of which you've already had a chance to read ahead for the homework problem is well. First of all, we're going to introduce Newton's law of universal gravitation, which is giving the force, the gravitational force between two objects depending on their masses and their distances. Then we're going to talk about gravitational force near the Earth's surface, and we're going to connect this back to what we know, what we've been using for weight and the force of gravity near the Earth's surface. And then we're going to talk a little bit about potential energy, which you've already read ahead in the chapter. So let's start with just a little bit of a historical overview. So gravitation is, of course, or the Newton's law of gravitation is the outcome of a long history of questions. When people were looking up at the sky and saw the planets move across the sky. So the question was, why do these planets move there? Are they gods, or is there some physical phenomenon that underpins their motion? And so this really goes back to Ptolemy, who made a model at that point still with the Earth at the center of the universe, and with the planets moving around in circles and in circles on circles and circles on circles on circles around the Earth in the center. That was called the epicycle model of the solar system, really. And then at some point Copernicus came along, a few 1,000 years later, and Copernicus proposed this heliocentric model of the universe, where he put the sun in the center of the universe, and now everything was moving around in circular orbits around the sun. And there was some data to of course support the notion that the sun is at the center of at least the solar system, although he still put it at the center of the universe as well. And that data came from a couple of astronomers, including Galileo, Kepler, Brahe. It really took Newton to not just look at this as let's put the sun in the middle and have circular orbits for planets, but to actually derive the underlying law of gravitational interaction, and to actually set up the mathematical tools to derive those orbits. And so Newton came up with the law of universal gravitation, and in addition also invented calculus to be able to determine the motions that the planets would actually take along the sky. So the law of universal gravitation that we're going to introduce here in a second is probably somewhat a side note if you compare it with the invention of calculus, but of course it's a very fundamental law. And as we'll talk about just later today, of course the story isn't done for gravitation. In the beginning of the 20th century, Einstein came along and he discovered described gravity in terms of general relativity. So the law of universal gravitation that we're talking about today isn't the end of everything about gravitation either. There's more detailed descriptions that we can come up with, which in certain limits revert back to Newton's law of gravitation, just like Newton's law of gravitation reverts back to the weight is m times g in certain limits. So let's look at the universal law of universal gravitation. So what it will describe is the force F12, which is the force from mass 2 on mass 1, when those masses are separated by a distance vector r12. This is the unit vector here, and the distance itself is r. So r12 is the distance from 1 to 2. r21 is the distance from 2 to 1. So obviously they're the same vectors with just a minus sign, different by a minus sign. So now we're going to write down the force between those two masses, and we're going to assume that the entire mass is in the center of mass of this point. So we only have to think about this as point masses, and that works well for small masses, small compared to the distance between the two. So Newton's law of gravitation, or universal gravitation, says that this force F12, the force from mass 2 on mass 1, is some proportionality constant times the mass 1, mass 2 over the distance between them squared, and it's in the direction of the vector between them, the unit vector between forces between masses 1 and 2. So this is the force by m2 on m1, and of course there will be an equivalent F21, which is g times m1 m2, and now this is r21 squared times r21, and as you can see, that's just exactly the opposite as F12. So the force by m1 on m2 is equal and opposite to the force by m2 on m1. So there's of course a constant here. This constant g is the universal gravitation constant, or also called big G, in contrast to small g, which is the 9.8 meters per second squared. So big G has a certain value, which has been measured in many lab experiments, and G has a value that is 6.67 times 10 to the minus 11, and there will be some units to it, because if we look at the units in Newton's law of gravitation here, the units will be force divided by mass squared times distance squared. So force divided by mass squared times distance squared. So those are the units of the universal gravitational constant. Gravitational constant. Why do we call it a universal gravitational constant? Well, according to everything we've been able to measure, this gravitational constant describes gravitational attraction from distances r12 on the order of millimeters all the way up to light years and millions of light years, or at least thousands of light years between the different masses. So that means it describes gravitation not just at one particular distance scale. It describes gravitational forces at all distance scales, or at least all distance scales larger than millimeters. And I'm not trying to make a big deal out of this lower limit. It just becomes very hard to measure gravitational forces at short distance scales, because not only does that mean that the distances are small, but it means in particular that those masses m1 and m2 are small. And so the way to measure this G in the lab, as opposed to from astrophysical observations, is using a device called a torsion balance, and the textbook has a picture of that. So we have a couple of big masses here, and then we have a suspended set of two masses, little masses here, that is hanging from a wire. This is actually an experiment that we do with the third and fourth year physics students in the lab on the fifth floor of the Allen building. So you can actually measure the effect due to gravitational attraction between the little mass and the large mass here, and the little mass and the large mass here. And as you can imagine, that attraction between the two masses will cause a torque on the rod that connects them. And when that torque is applied, it will actually rotate the little mirror here, and so you can actually see the light spot shift on a measuring stick that you put there. This is a very, very sensitive experiment, so usually this only gets done by students at night when no one's in the building, because if someone walks outside the building, there's so many vibrations that get introduced that the whole thing starts shifting around anyway. So the reason why this is such a hard experiment is because the gravitational attraction between these two masses is exceedingly small, right? These masses are maybe, I would guess the larger mass is maybe 10 kilograms. The smaller mass is, let's say, 1 kilogram. So what's going to be the forces if they're, let's say, 10 centimeters apart? We can plug in those numbers. So if M1 is 10 kilograms, if M2 is 1 kilogram, if the distance R12 is 10 centimeters or 0.1 meters, then if we plug that all in, the force F12 is 6.67 times 10 to the minus 11, and then we've got the product of our two masses, so that's 10 times 1 kilogram squared over the distance, 0.1 meter squared. Let me put the meter here. So what we'll find is that this is 6.67 times 10 to the minus 12 Newton. So that's, of course, a very small force, and that's why it makes it very hard to measure. And that's why in this particular setup, we actually, the students have to typically let this come to rest. There can't be any air currents. There can't be any motion outside the laboratory, because that can cause forces that are larger than the force of those two masses on each other. Obviously, one thing that is an advantage is that the force will apply twice between both of those sides of the torsion balance. But still, that doesn't make this a large force at all. And you can imagine that this will be very difficult to do at an even smaller scale. You certainly can't do this kind of experiment at scales that are micrometer or below, because then the masses become even smaller, the distances become even smaller, and so it becomes more difficult to make that measurement yet. So this gravitational constant has been measured using these tabletop type measurements, of course with more precision than what we can do in the lab in Allen. And then of course they've also been measured at large scales by looking at the attraction and the dynamics due to gravitational forces in the universe, because we can look at different galaxies, and we can see them move towards and away from each other or around each other, and that can tell us, based on their acceleration, that can tell us what the gravitational force has to be if we have a good estimate of the masses of those astrophysical objects. And that's where the difficulty lies in that particular type of measurements of the universal gravitational constant, because we can't just go to another galaxy and weigh it or decide what its mass is. We have to derive that from other measurements as well. So one of the things that is interesting in this gravitational force, and that is very common for forces in nature, is actually two things. One is it's a force that points towards the center, towards the along the line between the two masses. So if you think of mass 2, which is drawn larger here, as being the larger mass, then the force on M1 is always going to point back to the center of M2. No matter where you are, the force is pointing towards the center of mass M2. This is what we call a central force, not surprisingly, because it's pointing back to the center. And often it's visualized by drawing these kind of vector field diagrams. So this is a three-dimensional representation of what the force would be anywhere in space if you were to put a mass there. So if I were to put a mass at this particular point here, the force would point along that arrow. If I were to put a mass at a point closer to the central mass, then the force would be larger. So that's visualized by having a longer arrow. So this is a way of visualizing these central force vector fields. And again, that is something that we will encounter more often in not just in gravitational forces. So vector field visualization of a central force. The other thing that's very common in physics for these kind of forces is not just that they point towards the center or point along the line that connects the two masses, but is that it goes like 1 over the distance squared. So you can you can find this in other physical systems as well. Is that when we have a central force, it is common for it to be a 1 over r squared force. So it's an inverse square law on the magnitude of the force. Again, a very common scenario, and obviously that is not something we can demonstrate in this drawing here, but the force will go like 1 over the distance squared. That's very fundamental, and there's actually, we could go over some of the mathematical reasons for why that's the case, but it depends a little bit on the vector algebra and the vector calculus nature of these gravitational fields. So it's a little bit more advanced math than you've had at this point. But just keep in mind that central forces and 1 over square and an inverse square law forces are very common in nature, and so gravitational force is a good example of that. So Silas is asking, can lab setups be used to observe the true center of mass of odd shapes? Yeah, so this is a little bit not necessarily related to gravitation in the Newton's law of gravitation, but one thing you can do to calculate the center of mass is you can use the static equilibrium. If you have some oddly shaped object, you can just attach it to the ceiling here with a little piece of string, and it will orient itself such that the tension in that piece of string and the gravitational force are in the same line, that the line of action is shared there. The reason why they do that is because if that's not the case, there's going to be a torque that forces the object to orient itself this way. So if you do that a number of times, you can essentially take your object. Let me try to repeat the drawing. And so you'll find, for example, if you attach the object here, the center of mass has to lie along this line. If I attach the object here, the center of mass has to be along this line. If I attach the object here, the center of mass has to be along this line. And you can do that a number of times until, of course, you find exactly where the center of mass has to be based on the intersection of all those lines. So it's a good question. It's an example of where these torques and static equilibrium conditions can be used to determine experimentally the center of mass. Okay. So we've talked now about the gravitational force, the universal law of gravitation from Newton. And that's, of course, different from what we've talked about in the past. In the past, we've talked about gravitation and weight as the force is m times g. And how can that be the same as, or a description now, where this is g times m1, m2 over r12. And let me just write the magnitude here without the unit vector. So how, or well, let's write the unit vector, r12. So how can this be the same to that, right? So one thing we can do is we can take this expression here, and now that you've all had calculus, we can take this expression and expand it in a Taylor series. So if for force, and I'm going to use the magnitude now, so the magnitude of this force is g times m1. I'm going to write m1 is just the mass, and m2 is the mass of the Earth. So this is going to be the mass of the Earth, an object with a mass m in the gravitational field of the Earth. So we're going to have m, little m, times the mass of the Earth over r squared. Now what I'm going to do is I'm going to take r, and I'll write it as the radius of the Earth plus an additional distance delta r. So now we're not at the surface of the Earth, we're a distance delta r above the surface of the Earth. That's the surface of the radius of the Earth, and then I'll have an additional delta r that allows me to look at heights of buildings, for example. Something on a scale that is small compared to the radius of the Earth. So that's going to be g times m me over re plus delta r squared. Or g times m me, and that's going to be r. Actually, let me take out one of those, this factor re, so that becomes an re squared, and I'm left with 1 over 1 plus delta r over re squared, right? So I can write this as g times m me over re squared times 1 plus delta r over re to the power minus 2. And again, here, everywhere I've kind of assumed that, or I'm not assuming anything yet, but let's assume that delta r is much less than the radius of the Earth. So we're looking at small deviations of, or small changes delta r compared to the distance, the radius of the Earth. So now I can Taylor expand this term. And if I do a Taylor expansion, that's going to be, so the same prefactor here. So that Taylor expansion will be 1, and then I've got my exponent minus 2 here, minus 2 delta r over re. And I could keep going. I can write my second order term, which is 1/2 times this exponent times the exponent minus 1. So that's going to be a plus sign, and my exponents are the terms are going to end up being a factor 3 delta r over re squared, and then the next term is going to be a minus sign, and so on and so on. In any case, I'm not going to even bother about all of these additional second order terms. I'm just going to call them big O symbol delta r squared. So they're of order delta r squared. So and delta r squared terms are going to be much smaller even than delta r terms. So most of the interesting stuff is going to be in this term. That's going to be my first order term. This is my 0th order term. So if I write this all down, I now have g m e re squared. I'm going to put my m here. 1 minus 2 delta r over re. And this is approximately equal now. And that I can write as, we have the first term, which is g times m-e r-e squared times the mass. And then we have a second term that is going to be minus 2 times g m-e over r-e squared times delta r over r-e. So let's look at that in a little bit more detail. We've got here a factor that looks very similar to m times g if we set or g equal to big G times the mass of the Earth over the radius of the Earth squared. And in fact, if you calculate 6.67 10 to the minus 11, I'm not going to write my units here, times the mass of the Earth, which is 6 times 10 to the 24th kilograms, and you divide that by 6,370 kilometers squared. If you plug in those numbers, you'll find that this is about 9.8 meters per second squared. So G is actually something that we can write in terms of the universal constant of gravitation and the mass of the Earth and the radius of the Earth squared. So the other thing we can do, since we have the second order term, that actually now gives us an idea of how G changes with distance, with height, if or delta R becomes larger. So let's look at, so if we think of G as not just the zeroth order term, but we include the first order term, then G will actually be G times big G times me over re squared. And now I can go back to this term here. So it's going to be 1 minus 2 delta R over re. So that is G at a height delta R above Earth's surface. And I could do this more precisely by taking the third order term. And I can add additional terms to see how G really changes with respect to height. But this gives me a linear approximation. It's a linear approximation because I only have a linear term here, right? I'd have something that depends only on delta R, a first order polynomial, and that's because I did my Taylor expansion there. So I can look at that. Let's say, for example, we're a satellite at delta R of 400 kilometers height above the surface. Then what is G there? Well, G will be, this is my 9.8 meters per second squared. That's the prefactor here, that didn't change, times 1 minus 2 times 400 kilometers over 6,370 kilometers. And if you calculate that, you'll find that that's approximately, so it's going to be smaller because I take my factor 1 and I subtract the number that is less than 1. So you're going to find 8.6 meters per second squared. So G at a height of 400 kilometers is actually less than G at the surface of the Earth at a height of delta R equal to 0, where this term just drops out entirely. So G actually changes with height, and this sort of indicates the usefulness and a very fundamental point in physics, which is that our previous laws, which previously we said that F is equal to m times G, where G is 9.8 meters per second squared, that doesn't become invalid because we have a better law, Newton's law of gravitation, but it allows us to take this and take this description, which is only valid at the Earth's surface, and it allows us to extend the region in which we can talk about gravity. Now we can describe gravity not just at the Earth's surface, but also at different heights. We can actually describe gravity in a much more general framework, and so we extend the previous description of F equals mg to a much larger range of a much larger domain of applicability. And that's, of course, where then general relativity comes in as well. General relativity takes Newton's law of gravitation and extends the domain of validity of Newton's law of gravitation to a much larger domain. Now it will also apply very close to very dense masses, where we know that that Newton's law of gravitation actually breaks down. And in fact, Newton's law of gravitation breaks down already when, to some extent, to an observable extent, it breaks down when describing the motion of the planet of Mercury in the gravitational field of the sun, because they're so close together and the mass of the sun is so heavy. So there's different things. So this expression, this Taylor expansion, is one way to do this. Of course, we didn't necessarily need to keep all these higher order terms to just derive the fact that that the little g is related to big G, but this allows us to introduce sort of this linear approximation as one way to derive how G changes when you go to a different height. Okay. So there's another aspect to the gravitational acceleration at the Earth's surface, and that's related to the fact that the Earth is not standing still, but the Earth is actually moving around, right? So there's also going to be centripetal acceleration that that plays a role here. In fact, if we have a scale, let's start by looking at the scale on the North Pole here. On the North Pole, there's going to be a force that a spring, as part of a scale. There's a force that the spring exerts on this mass to pull it up, to counteract the force of gravity that is pulling down on that mass. So there's no rotation here on exactly on the axis. So the force and so gravity is pointing straight towards the center. So if this object on the scale is at rest in static equilibrium, then the force due to the spring will have to be exactly equal and opposite to the force of gravity, and so it will have to point exactly vertically upwards. There's no centripetal acceleration here, so these, Fsn will be exactly equal to m times g. On the equator, that's not the case anymore. Now there is a centripetal acceleration, and the centripetal acceleration is going to be related to the rotational the rotational velocity, the angular velocity of the Earth, and the radius of the Earth. So there's going to be a net centripetal acceleration, that is the difference between the force due to the spring and the force due to gravity. We can actually write that down. So at the equator, oops, where are we here? So let's call this weight at the Earth's surface. So at the North Pole, we just had that the force due to the spring is equal to m times g. At the equator, we now have that the force due to the spring minus m times g will have to be m times the centripetal acceleration. And the centripetal acceleration at the equator is going to be minus r times omega squared. So this is going to be minus m times r Earth omega squared, with omega is equal to 1 is equal to 2 pi over 1 day. And of course, that will correspond to some kind of radians per second a value. I think, forget what it is, 10 to the minus, 1 day is 86,400 seconds. So it's going to be something like 10 to the minus 6 radians per second. So that means that in this case, Fs, the force due to the spring, will actually be different, right? So this will be it will be mg minus mre omega squared. And so the weight that our scale will indicate, if we take our scale from the North Pole and take it to the equator, then if it's been calibrated at the North Pole to measure a mass of m when the force is equal to this magnitude, then now we will measure a different mass and we'll actually measure a lower mass. So this is one of the effects of the rotation of the Earth. Now the thing becomes even more interesting when we look at a non-zero latitude, because now the force due to gravity is pointing towards the center of the Earth. The centripetal acceleration is pointing perpendicular to the axis here. And so the force of the spring will have to be such that the sum of the force of the spring and the force of gravity add up to the centripetal acceleration. So that means at a non-zero latitude, we'll have, let's try to draw this. So if we're at this point here, for example, if this is the center of the Earth, that's our point P here. So we're going to have m times g, or the gravitational force that is pointing towards the center of the Earth. We're going to have a net acceleration that is going to be pointing towards the axis here. And now Fs, which is mg plus ac, will have to be such that so Fs is mg plus ac. Sorry, I'm missing a minus sign here. Mg, it's Fs plus mg, that is equal to m times ac. So Fs is m times ac minus m times g. So it's going to be minus m times g. So the Fs, in a very exaggerated way here, is actually going to point off of the vertical, or off of the line that points to the center of the Earth. It will actually be pointing along a line that is not going through the center of the Earth, but it is going through a point that is below the center of the Earth. And this will be what we will define as the vertical at that point on Earth. And it will actually look as though it is not going through the center of the Earth, but that's what effectively, because of the centripetal acceleration, that's what our vertical will be defined as. And the textbook makes a point of saying, this is the direction in which buildings are built at that point on Earth. Now, of course, it's also the direction at which locally the soil will settle perpendicularly to. So it doesn't necessarily make as much sense to think of these buildings as being tilted. But it does make sense to now think about what the effect is of this on the shape of the Earth, because what will happen is that it will make the Earth want to be flatter at the poles and bulge out more at the equator because of this effect of centripetal acceleration. And if we had a perfectly fluid liquid Earth, then we would end up with an equilibrium shape here, where the surface of the Earth is everywhere exactly perpendicular to the direction of that local vertical vector that takes into account the centripetal acceleration. Okay. So then one thing that you did already read is, of course, gravitational potential energy. you needed for today's problem, and that of course is something that we derive from or general expression for potential energies, which is the integral of the force times the distance when we take a path from R1 to R2, some vector R1 to some vector R2. And the textbook goes to a little bit of a derivation of this. And again, we can introduce a potential energy with any reference point, but in this case, it makes sense to put the reference point U ref is equal to 0 at a position that's infinitely far away. And with that assumption, we can set, we can write down or expression for the potential energy of a mass m, little m, in the gravitational field of the Earth as this 1 over r law. So now this is 1 over r, not the 1 over r squared dependence. So for the potential energy at a distance r away from the Earth, or from any large mass, maybe I should remove the little e here. So the potential energy for an object a distance r away from a large mass will be given by this expression. So in okay, so Isaac is asking whether mg should be negative here. So I've written it as a vector equation. So in the case of vector equations, it actually has to be positive, because this is the sum of all of the forces. If I were to write it in coordinates, then I would have to take care of my negative signs. But I'm not writing it in terms of coordinates because it would be difficult to write it along a single coordinate axis, in particular in this case of non-zero latitude, because all of the vectors are pointing in different directions. In this case here, I wrote it as a scalar quantity, not as a vector quantity, because everything is along the same direction. At the equator, everything is along the same direction. mg, the centripetal acceleration, and the force due to the spring are all along the same direction. I hope that makes sense. Okay, that's it for today. So we're going to continue that gravitational potential energy, total energy, energy conservation, and then we'll continue through Kepler's laws of planetary orbits, and we'll do things like Hohmann transfers and delta V's on Friday. Okay, that's it for today.